Thank you to Brilliant for supporting PBS. Some things really do seem to be impossible, like faster than light communication, or breaking the second law of thermodynamics, or learning the second law and not being forever haunted by the whisper of the heat death. The universe seems to conspire to thwart any attempt to do certain things. And for a while, it seemed like the quantum structure of space-time might be part of this forbidden knowledge. But now, research has found ways to trick the universe into revealing its quantum underbelly. We've got a couple of quick announcements before we start. First, our eternal battle against the algorithm continues. The best way to encourage YouTube to share our videos is to like and comment. Doing both really makes a difference. And if you're new here, subscribe, hit the bell, and introduce yourself in the comments. We're friendly. Next up, we're excited to launch our Composition of the Universe nickel and enamel pin, now with a holofoil backing. If you want to flex your knowledge of dark energy, dark matter, and the terrifyingly small slice of ordinary matter that you and our world is made of, check out our first pin of 2026. And if you prefer your mornings fueled by dark energy, we've also got a brand new dark energy mug. Plus, our UV Glow Kerr rotating black hole hoodies and shirts are still available. Everything is 10% off until February 9th. Links in the description. Now, onto the episode. Recently, we looked at whether nature has a hard rule against measuring the graviton, the quantum particle of gravity. By some approaches, directly glimpsing this building block of space-time seems fundamentally impossible. But we also saw that there are other methods that are just so stupidly difficult they might as well be impossible. They seem to involve using planet-sized graviton detectors and even stellar corpses as graviton sources. Sounds disheartening. Well, maybe we have to wait millennia until we can build our astro-engineering superstructures, or maybe we can just get cleverer today. In recent years, theoretical and experimental developments have made it possible to conjure up new ideas for detectors. One such possibility is the use of quantum sensing, outlined in a paper by Bahar, Manikandan, Badal, and Pikovsky, submitted to Nature in 2024. In the previous episode, we talked about a family of experiments that work by treating the graviton as any other particle. So rather than trying to detect its infinitesimal gravitational field, we instead try to spot a more direct interaction with another particle, similar to how we do with particle colliders. When we account for the extreme low probability of such an event, we found that we needed these planet-sized detectors and stellar graviton sources to even have a remote chance at it. In order to claim that we saw a quantum of gravity, these sorts of detectors require that the graviton interact with another quantum particle. Now, elementary quantum particles are tiny, and gravity is incredibly weak. Combine these two, and the graviton has only a minuscule chance of having a sufficiently head-on collision with such a particle to produce the sort of interactions that we need. Now, we can't do much about the weakness of gravity, but what if we can make a quantum particle bigger? What if we could make one that's human scale, that's macroscopic? That's what this new paper proposes with its resonant mass detector. It'd work like this. Cool a metal cylinder to as close as possible to absolute zero. In that state, there's almost no motion in the individual atoms in the crystal lattice. There's also almost no energy in the global oscillations of the metal in its vibrational modes. At sufficiently low temperature, those vibrational modes are quantum states. They increase in discrete steps, quantum jumps, just as an electron jumps up in discrete energy levels in an atom. These individual quantum vibrational modes are called phonons. They're like a quantum of sound. Now, these are going to be our macroscopic quantum particles, these phonons. And they will have a vastly larger cross-section or probability for interaction with a graviton than does a single electron. So when a graviton passes by, there's a tiny but no longer unthinkably tiny chance that it'll excite a phonon. Then, using quantum sensing techniques, this phonon can in principle be detected. And that could be considered the detection of a graviton. There are of course one or two complications. To even get our cylinder into its vibrational ground state, it needs to be cooled to a small fraction of a single Kelvin, and I'll come back to the exact number and the plausibility later. But even having achieved that, most of the phonons generated in the detector will not be due to gravitons. The excitation energy of a single phonon is so small that any source of noise can produce one. That includes the thermal fluctuations that we are trying to minimize, but also seismic noise, cosmic rays, electromagnetic interference, internal material defects, and feedback from the device that we're using to measure these phonons. Try as hard as we might, it's not feasible to reduce noise to the level that gravitons are the main source of detected phonons. But what if somehow we had an independent way to know that a sudden flood of gravitons had passed by our detector at the very instant that a graviton was detected, and we knew that those gravitons were of the exact frequency as our excited phonon? Well, assuming that we got our noise down low enough, that would probably give us a lot more confidence that we'd actually succeeded in detecting a graviton. And this is the other brilliant part of this proposal. We actually have a way of doing just that. In 2015, we detected our first gravitational wave from merging black holes with LIGO. Since then, we've detected hundreds. If gravitons are real, then a gravitational wave really is just a coherent flood of many gravitons, similar to how a laser is a coherent beam of photons. A gravitational wave from a black hole merger might contain 10 to the power of 36 gravitons, and those gravitons will share the same well-defined frequency as the gravitational wave that they're part of. Now, this is starting to all come together. We build a cylinder with mass and dimensions to support a vibrational mode with frequency equal to an expected gravitational wave frequency. For a neutron star merger, like the ones we've seen with LIGO, a possible candidate would be a beryllium bar of about 15 kilograms. Alternatively, to detect a graviton from a black hole merger, a niobium bar weighing around 10 tons would have the right properties to be excited by a graviton with the right frequency, around 175 Hz. The bar would then have to be cooled to 1 millikelvin. Now, this is colder than what we are currently able to achieve. At best, we can manage a few hundred millikelvin. Proposed experiments get us a bit closer, so this might be viable in the near future. Once the cylinder is attached to our phonon detector, we'll start to get frequent clicks of detection. Now, almost all of these will be due to the various sources of noise, but eventually an excitation will occur at the exact same time that LIGO detects a gravitational wave of the same frequency. And as long as the noisy excitations are rare enough that such a coincident detection is unlikely, then we can hope that we've actually detected a graviton. And this brings me to the other main hurdle: continually measuring what would be an extremely delicate system without ruining the precision of the measurement or the quantum state. Since we don't know when a gravitational wave is going to hit us, the experiment needs to run continuously, and it needs to very weakly monitor the cylinder, checking for an excitation. We're also not there yet with the quantum sensing technology needed to do the delicate continuous monitoring, but it's something that's maybe just decades away rather than millennia. Okay, so we build the detector, we detect the bar shift into a higher frequency level, and this coincides with a LIGO detection at the same frequency. Does that mean we've finally definitively detected a graviton? This is where things get a little muddy. If gravitons exist, then yes, the click was probably due to an actual graviton. But that's not the same thing as a formal discovery of gravitons, because there are ways that gravity could have made the click happen, even if gravitons don't exist at all. Now, to explain that, I want to go back to the phenomenon that started this whole forces as quantum fields business, the photoelectric effect, which is often described as providing proof of the existence of the photon. It goes like this. Take a pair of conducting plates with a gap between them and shine a laser at one plate. energy from photons in the laser can be absorbed by electrons in the plate, allowing them to jump between the plates and resulting in a measurable current. Now apply a voltage across the gap, so the electrons need a minimum energy to make the crossing. Before we knew about photons, you might think that as long as the laser was bright enough, it could provide the needed energy to cause a current. But instead, we find that if the frequency of light is below a certain threshold, no electrons will jump the gap. It doesn't matter how bright you make the laser or how long you shine it for. Now, this makes sense if we say that 1, the EM field of the laser is made of individual chunks, 2, those chunks have a specific energy defined by the frequency, and 3, an electron can absorb only a single chunk in order to make its jump between the plates. Low frequency light, no matter how intense, just doesn't contain photons with enough energy to cause a jump. This is the line of reasoning usually used to explain why the photoelectric effect constitutes the discovery of the photon. This is wrong. The photoelectric effect is really the discovery of quantum energy levels in electrons. That's because there is a way for a purely classical EM field to deliver its energy to enable a quantum jump. A classical field is able to deliver that energy in arbitrarily small portions. It doesn't do this by delivering tiny bits of energy over time, but rather by slowly increasing the quantum probability of a jump. It's technical, but the point is that the photoelectric effect didn't really constitute the discovery of photons, it discovered quantized energy levels in atoms. Okay, so why the tangent to the photoelectric effect? Because the same reasoning applies to our graviton experiment. The way I described it, a single graviton with the right frequency excites a phonon of the same frequency in the metal cylinder. But even if the gravitational field is not made of gravitons, if it's really classical, it can still excite that phonon by slowly increasing the excitation probability as long as it has the right frequency. Now, this is a subtle point. If gravitons exist, then the clicks from a resonant mass detector coinciding with the right gravitational wave are almost certainly graviton detections, which is amazing because we didn't need a planet-sized detector, but they don't prove that gravitons exist because there's another potential explanation. So how do we proceed? In the case of the photoelectric effect, we were able to prove the existence of photons with a much more sophisticated experiment that involved preparing the EM field so that it would be in a non-classical state, if it is indeed a non-classical field. For example, extremely low intensity lasers so that the plate is hit by just very few photons at a time. Then you can tell from the distribution of energies of excited electrons whether the EM field is fundamentally quantized or smooth and classical. And so in principle, this can be done with gravitons too, except that now we're back to the realm of how the hell do we do this? There are no natural source of non-classical gravity, and certainly none of single gravitons. Now, we may still need to build a graviton source rather than relying on natural sources. So, are we back to the drawing board? Not quite. Our detector did just get an insane upgrade, and so the burden of the challenge now seems to lie in the graviton source, and perhaps some unexpected result will show up. Or we could actually go back to the drawing board and get even cleverer. A recent paper by Ralph Schutzold proposes an optical Weber bar instead of a solid resonant mass. In this experiment, you use laser pulses in an interferometer-like geometry so that a passing gravitational wave can transfer a tiny but lasting amount of energy to the light, which then shows up as a measurable phase shift. Unlike LIGO, which reads out a phase change caused by changes in the arm lengths as the wave is passing, this scheme aims to convert the gravitational wave's time-dependent modulation into a permanent frequency and energy shift of the photons, and then amplify the resulting phase difference over a much longer period of time. In graviton language, that net energy exchange can be described as stimulated emission or absorption of gravitons by the light. And analogy of stimulated processes in quantum optics, so it's kind of like lasing the gravitational wave itself, although the effect is observed in the light, not in the gravitational waves. As with the resonant mass detector, the energy transfer alone wouldn't be enough to prove that gravity is quantized, but this scheme offers a way to at least see the signature of quantum gravity. If the light is prepared in a strongly non-classical state, then energy conservation ties the photon state to the gravitational field's own energy, and this could put the gravitational wave into an actual quantum superposition, which would reveal itself in aspects of the phase of the interferometer beam. And if a gravitational wave could be in a quantum superposition, then it must be quantum. The baseline optical Weber bar might actually be feasible with present-day interferometric tools, while the genuinely quantum gravity-sensitive version demands a much more extreme quantum state preparation and readout, and is even further away than the resonant mass detector. So yeah, the universe wanted us to believe that we could never hope to glimpse the quantum nature of gravity. Like it's embarrassed or something to have us peer too deeply under its kilt to see how the sausage is made. And while it's going to be a long time before we can both catch a graviton and be sure that we caught one, there are some brilliant experiments that we could do much sooner, in some cases now-ish, that may let us tease the quantum out of the classical seeming fabric of space-time. Thank you to Brilliant for supporting PBS. Brilliant is designed to help learners improve in math and computer science with visual interactive problem solving and personalized practice. It starts you at a personalized level based on your background, designs practice sets, and reviews your comprehension, and allows you to advance at your pace. Each lesson starts by helping you master the foundations and offers a mix of interactive problems, motivating challenges, and encouragement to keep you moving forward. And if you're into math, Brilliant offers a course on quadratics, where you'll learn to work fluently with quadratic expressions and equations. In the course, you'll tackle everything from multiplying expressions to factoring expressions to solving quadratic equations. To learn for free on Brilliant for a full 30 days, go to brilliant.org/spacetime or click the link in the description. Brilliant's also given our viewers 20% off an annual premium subscription, which gives you unlimited daily access to everything on Brilliant.